So now we're going to talk a little bit about phase in the light wave. So waves have certain properties, amplitude, and frequency, but one that's going to become very important here in a minute is phase. And so you can just think of phase as the location of one of the peaks. But what we really want to know, what is really important, is something called phase difference. So if you have two different waves, they're superimposed on top of each other, the fact that the waves don't line up, and these waves have the same frequency and they have the same amplitude in this case, and we can see that these peaks don't line up, and we call that a phase difference or phase shift. So if we're talking about the y components and the x components being the same but actually having a certain phase shift, this can lead to something called circular polarization. So here's an example of a phase shift. So before, there was zero phase shift between the x and y components, but here there is a 90-degree phase shift between the x and y components. So you see before they were always at a max together and zero together and a min together, but here you can see when red is at a peak, blue is at zero, and when blue is at a peak, red is at zero. And the same thing, and it kind of oscillates around, so that the sum of these vectors, the length of that resultant vector is always constant, but the effect is it kind of corkscrews around, as you can see here.
Let's reintroduce the idea of indices of refraction and therefore Snell's law. And Snell's law basically says that different materials cause light to travel at different speeds within them. And the reason that light travels at different speeds is because the materials have a different index of refraction. And this change in speed causes the light to bend. So when you look into a pool of water, the bottom seems closer than it actually is. A birefringent material has indices of refraction that are different in the y direction and x direction. So we see in this picture here, we have ny, which represents the index of refraction in the vertical direction, and we have nx, which represents the index of refraction in the x direction, the horizontal direction. And these two in a birefringent material are not the same. And this can lead to some pretty interesting effects. So here we have a block. Down in the bottom, we have a block of birefringent material, and we have a wave that's 45-degree linearly polarized. So we have equal horizontal and vertical components. And let's take a look. Well, all we've done here is taken that 3D image and made it 2D, and that's what we've pasted up in the upper right. And the blue is vertical, the red is horizontal, but we've just made them so they're easier to look at. And you can see before they enter the cube, they are in phase, meaning their peaks are always aligned and their zeros and troughs are always aligned. And when they go into the crystal, the vertical blue light, since it's polarized vertically, that portion interacts with the index of refraction in the y direction, and the red light, the horizontal light, that interacts with the index of refraction in the x direction. And since those aren't different in a birefringent material, the speeds at which those waves travel in that medium are also different. And so we see the blue travels a lot slower, which gives it more time to oscillate within the crystal, whereas the red moves a little quicker than the blue and doesn't oscillate as much. So by the time they leave the crystal, we see that at the moment when they leave, the blue is at a zero and the red is at a minimum. And so now we say they're out of phase, and you can see that that trend continues. When red is at a zero, horizontal is at a zero, the blue is at a peak or a minimum. And this leads to what we call circular polarization, or maybe some other polarizations basically, but circular polarization is the extreme. And so what we've done here is shown you those animations together. So we've already looked at these, but what we really want you to take away from this is in the top one, the circles are always together. They're always at a minimum or a zero or a maximum, whereas in the circular case, the result in the yellow vector is always is constant. It's always at a maximum, and it just rotates around. But the blue and red still they look almost identical to the previous case. They've just been phase shifted. And so when the blue is at a maximum, the red is at a zero. When the red is at a maximum, the blue is at a zero. and this is circular polarization. So now that we've talked about linear polarization and we've introduced you to circular and different types of polarizations, we're going to do some experiments and some demonstrations with birefringent materials. So to start, we're going to go back to our setup. So here we have just a linear polarizer over a unpolarized source. So remember, the monitor is unpolarized, and this is just the linear polarizer here. And birefringent materials come in all kinds of shapes and sizes, and they might be a little more common than you might think. So here we just have an ordinary protractor. It's plastic. It's got a little blue tint to it. But if we stick it on our linear polarizer here, we see that nothing's happened. It looks just as you'd expect. But if I take this off, just for effect here, and take our polarizer that's crossed and put it on top, so we've got basically no light coming through. Let me make sure it's oriented well. And now I take the same protractor and I put it in there, and we see a whole different effect. We've got all sorts of light coming through, different colors, dependent on where on that protractor it's coming. So we've got some spatial dependence in there. And it looks pretty cool. It's a cool looking object. And we know it's got birefringence because it's letting light through. Okay? And I'll put that back in a moment, but I want to show a different example. And that's with just a plastic bag. So this is a plastic bag that we have, and we can see if it's got some birefringence to it. And so I put it in here, and all of a sudden we just get white light coming through, and a lot of light. And then as I rotate it, the amount of light we get through varies. And this is really important because a birefringent material needs to be angled properly in order for that light to be able to rotate the way we want it to. So if you put a birefringent material in there and you don't rotate it correctly, you're not going to get much light, if any, through. And so this is clearly birefringent because as I rotate it, we get light coming through. And when I rotate at different angles, we don't. But a cool thing about these plastic bags is we can introduce some stress to them. So I'll just kind of start to try and tear this bag a little bit. I'm not going to tear it, but I'm just going to apply some stretching to it, stress. And I've done that to a few points. You can maybe see it there. And as I put that in there, now we've got some colors coming through. And that's kind of the same idea behind something like a protractor. Just from the way that these are constructed, there's some plastic going there, and as the plastic, there's some plastic form that's being made, and as it cools, it might cool non-uniformly. And that non-uniform cooling causes these spatial variations at the molecular level. And that kind of helps one color make it out, twist to the right orientation to make it out of that second polarizer as opposed to another color. And as I rotate this now, you'll see the location of those colors might change a bit. So as I rotate it here, no, we don't really see it here. So let's try it on the protractor. It's a lot clearer when I do it on here. So as I rotate this, you can see it looks like those colors are kind of moving, almost like a wave or ripple in the water. They just kind of flow from one location to another. And that's because now as I rotate this material, those birefringent properties are a little different spatially, just on the molecular level, very, very small differences, but we can see it because the wavelengths of light are very small, so any minor imperfections come out. But there are some other birefringent materials that we can look at, or maybe some materials that we might expect to be birefringent look like they might be birefringent but actually aren't. So here we have a broken CD case. So let's see what this looks like. So we get some colors coming out of there. And again, as I rotate it, we get different colors in different locations. And right here, there's a pretty noticeable spot. And it looks like a lot of colors are coming out of there. There's a lot of small, quick changes. And that's probably where this piece of plastic was injection molded from. So that's where they were sending the plastic into the form. And so that place kind of cools differently than everywhere else. And so that's why all those colors are coming in there from the stress birefringent process. We've also got another CD case. Let's see how this one turns up. Some colors, not quite as interesting as the others. This one looks like it might be birefringent, and when we put it in our material, we see light coming through, so we might suspect that there's some birefringence. But as I rotate this, it's not changing, which tells us that it's probably not birefringent. And maybe all it's doing is, as light comes through it, polarized light comes through it, as it tries to go through that material, it just gets depolarized. So then we get X and Y and maybe some circular polarization, all sorts of weird stuff happening. But it's not really just rotating it in a very uniform way. It's just kind of scattering it ununiformly. And so one of the guys in our lab, he was working with heating materials that wouldn't normally be birefringent. And so what he's done here is he's drawn out MSU in a marker, and then he's taken a heat gun to it and traced out those letters with a heat gun. And so what he wanted to see is, as it cooled, would that non-uniform cooling introduce some birefringence? And so let's see what happens. It's a little bit big for this, but we can definitely see some birefringence around the letters. And over here, kind of away from all the heating, there's not a lot of color, but right around the outline of these letters, we get a lot of colors coming through. So we can start to see that, yeah, maybe this is birefringent induced from stress, from heating. This one, he did the same thing. You can't really see any imperfections in this, but if I put it under here, there's definitely a stripe right down the middle that he took a heat gun and caused these non-uniform heating effects to take place. And as I rotate this, we get light in and out. This one's really cool because it basically goes dark, and then we get all these colors back, and then it goes dark again, and we get these different colors moving around a little bit. But mostly we just get light out or no light out. And let's see, we have this piece, which is a piece of plastic, but you can manufacture the birefringence to be at a very exact to cause a very exact orientation change in your polarization. So these pieces of birefringent material have been engineered to create circular polarized light. So if I put it in here and rotate it, we get light out, and then we don't when I have it rotated at the wrong angle. And so this is specifically made to do this kind of stuff. And that's really popular. It's a really important thing for all sorts of applications. Camera filters, for example, use them. Circular polarizers, that is. And that's why you need these kinds of engineered materials. Not, this protractor has some birefringence to it, but it's kind of accidental. It's not intended. But we can intentionally engineer birefringence so that it has some use for applications we may have.
So now that you've seen this demonstration, let's actually just talk a little bit more about what you need to see this birefringence. So we saw that in the demonstration, Martin had always two polarizers with a little space in the middle. So because seeing birefringence requires some sort of polarized input. You have in this example, we have unpolarized light going through a polarizer, so now it's polarized, hitting a birefringent sample, which rotates some of the polarization and comes out the other polarizer. Now, this doesn't necessarily, your setup doesn't always have to look like this, but this just means that your birefringent sample has to be illuminated with some sort of polarized light.
And here we see some images from similar to what we had in the demonstration. It's the same protractor here, pointing out that the stress points, so the corners, produce a lot of light, a little more light than other areas, and that's because we saw stressing a material can cause it to have birefringent properties, and therefore we get these colors coming out of it. And here we have just a standard piece of tape reel, or a tape dispenser rather, and there's a lot of cool things happening here, but this one shows the stress a little bit better. You see this point over towards the right where there's just a lot of color variation over short distances, which leads us to believe that that's kind of the point of the plastic injection molding was happening there, or that was the entrance point. And due to the strange cooling effects or the non-uniform cooling effects, we get these birefringent properties.
So here's an example where we have this case, this plastic case on the table, and on the left you see there's no filter on the camera and you can't really see anything, and on the right you have a polarizing filter and you see this great rainbow effect. By now you're familiar with, it must mean there's some sort of birefringent thing happening there. So, but earlier we talked, we always had two polarizers for this, but here we only have one on the camera, so how can we see this effect with only one filter? And the answer is because I didn't say that there always had to be two polarizers. I said that there had to be, your birefringent sample had to be illuminated with polarized light. And in this case, the polarized light is coming from the table. Unpolarized light is reflecting off the smooth surface of the table at a wide angle, which is creating polarized light, which then passes through the birefringent plastic, and then passes through the polarization filter on the camera, and that's what allows us to see the birefringent effect.